The Buckingham pi theorem allows you to have a general process to find a simplified or a more condensed functional relationship between an important parameter that you want to know and how to scale it larger or smaller. So there is an enormous list of dimensionless numbers. A lot of them are used in fluids, but there's many more in other fields that can be explored. Those are going to be a Wikipedia page as referenced in the notes. I'm not going to write that on the board, but review the notes and you can review all and see all the different types of dimensionless numbers. So, the correct use of dimensionless numbers comes from a function of two simple things. The first is a further study in that field that you want to investigate, and this class is in fluid mechanics or thermal fluids, so would be further studies in engineering. There's also chemistry and any other use of dimensionless numbers, but there's further study needed in any one of those subject areas. But also, you need experience using those numbers and determining which correct dimensionless number to use, and that also comes from working with a mentor in that field, or a mentor engineer. So again, since this is an engineering class, an introduction to engineering class, further studies in engineering, and then experience working with a mentor engineer. Review the different dimensionless quantities on the Wikipedia page referenced in the notes. I'll go over a few of them here, specific to fluids. These will be fluids mechanics and fluid dynamics. We'll get into in the thermal portion of this class. Will come, and then there'll be important thermal parameters, but we'll hold off on giving you those dimensionless numbers. Since now we're dealing with forces and reaction to those forces, we'll give you a few of these dimensionless numbers. So again, we've already went over Reynolds number, which is going to be the comparison between inertia and viscosity. Inertial forces and viscous forces. This is always Reynolds number is always important. Different dimensionless numbers have very, very specific importance. So in fluid mechanics, fluid dynamics, Reynolds number is always important. Mach number. Mach number is going to be the ratio between the flow speed and the speed of sound, or how fast an object is moving in the fluid. So flow speed divided by the speed of sound. This is important in when your fluid is going to be compressible. Air is very highly compressible. So Mach number is going to be important when you get to very, very fast velocities compared to the speed of sound. Last is the Froude number. Froude number is going to be a ratio between the inertia forces and the gravity forces. And this is going to be important when you have a free surface, anywhere that you could have waves. So, free surface, potentially a ship on a free surface that you would have. As long as you have a free surface, the Froude number should be investigated. All right, let's do an example problem using the Mach number. So you probably have heard from movies and such, it's going Mach 3 or 0.8 Mach. So this is where those numbers come from. So let's calculate the Mach number for a plane traveling in air if the speed of sound is 313 meters per second. Mach number is the velocity of the flow, or the object moving in the fluid, divided by the speed of sound. So for a plane traveling at 270 meters per second, the Mach number is 0.86. If the plane is traveling, however, at 3,100 meters per second, and again the speed of sound is 313, the Mach number is 9.9. 9.9, the flow is going to be considered hypersonic. 0.86 is going to be considered subsonic. So a plane traveling at 3,100 meters per second is a hypersonic situation. Plane traveling at 270 is going to be subsonic. Okay, that concludes the lecture on dimensional analysis and similarity.